All right, so this video should be a little bit shorter than the other ones were because all we're going to talk about in this is what's called the combined gas law. The combined gas law combines the others together. So, I forgot to turn off the light. So, it's really simple. We had pressure and volume and temperature could all be adjusted. In the other ones, something was remaining constant. But in the combined gas law, nothing stays constant. Everything is changing and it becomes this ginormous, crazy, what just happened? And so we need to go through that. But before we do that, you all said you wanted to hear a joke. You didn't want to just be bored. So here's your joke. I even wrote it down so we can make sure that you understand what I'm saying. So it said, this girl said that she recognized me from the vegetarian club, but I swear I never met herbivore. All right, so here we go. Why do we need the combined gas law? Well, like I said, sometimes all the variables can be adjusted. So we have P1, V1, and T1. Remember before, we had pressure and volume for Boyle's law. We're inversely related. When one went up, the other goes down. And volume and temperature were Charles's law, and pressure and temperature was Gay-Lussac's law. So all we did is we just kind of took them and went splat, merged them together. So it's pressure 1, volume 1, and temperature 1, all equal to pressure 2, volume 2, and temperature 2. Again, I didn't write it, but you should recognize that these are being multiplied together and then divided by the temperatures on the bottom. And as you can see from the big giant red word pointing across, it must be Kelvin. If you use Celsius, it will be wrong, people. It will be wrong. Don't use Celsius. They're going to give you Celsius in the problem. Don't use Celsius. You've got to convert to Kelvin. So now, this is what it looks like. But a lot of times, it's easier to just already cross-multiply and get it out of the way so that we don't have this fraction thing. Algebra, you're all like, math, it's hard. So instead, I'm going to show you what it ends up looking like. If we were to cross-multiply, T2 goes with those guys. So all I'm going to do is I'm going to pull these down. P1 times V1 times T2. All I'm doing is I'm pulling that thing, I'm multiplying it by that side to cross multiply, right? You know the whole cross multiply thing? So it's P1, V1, and T2 is equal to P2 and V2 and T1 because again, T1 got multiplied by these guys. This expression right here might be a little bit easier for many of you to deal with, where you already have pressure, you have volume, you have temperature, and all you have to do is plug them into where they go. Please, 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 please remember, this is T2 and this is T1 now. It is not P1, V1, T1. If you're doing T1s, it looks like this. If you're doing where did it go? We lost our T2. What just happened? There it is, our T1. Whew, that was scary. So P1, V1, T2, P2, V2, T1. This is the mathematical side. If it's all being multiplied, totally up to you. If you know how to do algebra, then you just plug numbers in and solve. So for this, because that's all we have to do, I'm only going to do one sample right now. We will do some more samples in class because these are just taking Boyle's, Charles, and Gay-Lussac's and blending them all together where everything changes at one time. So here's our sample problem. It's big, lots of words. I don't even know if you can see them all on the screen. Let me get close. Looks good. Okay. A 400 liter, and one other thing I meant to do about that, I forgot to type that when I was typing it out. That's supposed to be a decimal. That's 3 significant figures. A 400 liter weather balloon is launched from LNHS at 17 degrees Celsius and a pressure of 785 torr. As it rises, the pressure drops to a pressure of 622 torr, and the temperature also drops to 4 degrees Celsius. What is the new volume of the balloon? Before I turn the page, on this page right here, we are going to identify the variables P1, V1, T1, P2, V2, and T2, and then we'll go to the next slide and we'll see what's going on there. So what is this first thing? If we just work through this one at a time, what is 400 liters? A 400 liter balloon is launched, blah, blah, blah. This is V1. That is our initial volume of our balloon. Volume 400 liters. It is launched from the school at, here's 17 degrees. This is a temperature, but what's wrong with this temperature? That's right, we can't use Celsius. Let's go ahead, before I even move on, I'm just going to write it right underneath this. 17 degrees Celsius plus 273 is 290 Kelvin. 290 Kelvin is more important than 17 degrees Celsius because when we do the calculation, must be Kelvin. 273 plus 17, 290. And a pressure of, that's pressure. Hopefully you recognize this is going to be P1. So I have V1 and P1 and T1. We're good for the first half. As it goes, notice the pressure is changing. Pressure drops. Here's our new pressure. P2 is 622 torr. And the temperature also drops. So this is now our new T, but 273 plus 4. We're going to go with 277 Kelvin for T2. And then it says, what is the new volume? That's V2. So again, as we look at these problems, you've got to be able to read the question, pull out the information that is important. You need to know the units of volume, the units of temperature, the units of pressure. As long as the units for pressure and volume are the same on both sides, it doesn't matter which unit we're using. As long as the units are the same, it can be in torr, it can be in whatever pressure unit we want, they just have to be the same on both sides. If they're not the same, you have to convert one of them like we did in the last video. So now that we have all of this, again, they gave us torr, we got temperature, we got volume, we're good to go. We're just going to take these numbers and plug them into our combined gas law mathematical equation of variables, and it looks like this. P1 and V1 and T1 are these values. We just identified these on the previous screen. P2, V2, and T2 are identified here. We don't know our new volume. So without knowing the volume, we got to plug and chug, solving for V2. So here's what it looks like. I took the 785 times 400 divided by 290. We took 622 times our unknown volume divided by 277. And then this is where, if you had done it the other way, this would be P1 times V1 times T2 equals P2 times V2 times T1. And when you do all of that mathematically, you rearrange and solve. This, again, this is where, as a chemistry teacher, I really struggle because this is not teaching chemistry right now. This is teaching math. I don't teach math. I'm not a good math teacher. I'm a pretty good chemistry teacher. I'm not a great chemistry teacher. I'm a pretty good chemistry teacher. I can understand what's going on. We can do math. You've got to be able to do the math to do these problems correctly. So one last thing to talk about here. The reason we need the combined gas law is what happens when multiple variables are changing. So remember when we've been talking about the kinetic molecular theory. In this case, our pressure went down. Remember, if there's less pressure, we would expect less collisions, and the volume is going to do what? If the pressure goes down, the volume should also have gotten bigger, right? There's fewer collisions, so less pressure means we're getting bigger. But what happens with the temperature? The temperature is going down. That means the particles are slowing down. So we're giving them more room, right? More room means less pressure. Wait, I'm saying that wrong. No, less pressure. Less pressure means more volume. There's fewer collisions, which means there's bigger volume. But a lower temperature means they're moving smaller and it's getting smaller. So we don't even know which one's going to win because they're both doing the opposite thing to each other. The bigger or the lower pressure makes a bigger volume. The lower temperature makes a smaller volume. So that's why we need this expression. We plug everything in, we do some math. And again, when we look at this, hopefully I'm going to pause for a moment and then you should do the calculations, multiply, divide, come up with an answer. Here we go. Did you get this for your answer? You should have got 482 liters. If you did not get 482 liters, then you need to go back and figure out what happened. In this specific case, the temperature drop was very, very small. So the volume going down was not as great as this huge pressure change, right? Percentage-wise, this is a much bigger percentage of pressure change than the percentage of temperature change. So it makes sense that our volume got larger. Again, in class, I will pull up a couple more questions. We'll do a few more samples together. We'll do them all kinds of different ways. We'll plug them in this way. We'll do the P1, V1, T2 equals P2, V2, T1 way. We'll do lots of different ways of solving these problems. Combined gas law is not ridiculously hard. It's just a lot of math. Those of you that say, I'm really bad at math, I understand that. We're going to work with you. We're going to get you the support that you need because you need to be